begin this presentation on sensor filtering in FRC. I'm James Kuzma. I've been a mentor on 971 for a few years after having been a student back in 2011-ish. And I am one of the software mentors on 971. That is also pretty much what I do in my day job. So, why are we here? You may or may not have read I don't know how good the description of this talk was. I think I made it reasonable. But you want to be able to control your robot. You want to be able to have your mechanisms move how they're supposed to. You want them to move quickly. You want your robot to be reliable. In order to accomplish that, the software on the robot needs to know what the robot is doing, which can mean different things. There's also some things you may not need to have the robot know about. So, for instance, you might need to have the robot spin a wheel up to a certain speed. This is common in years where you need to shoot a ball into a goal. You may need to move some elevator to a certain height. Many teams would have needed that this year. You might want to have the robot drive to a particular position on the field. That would be common this year for trying to place a game object. There's also things like you might want to know where you are on the field so that you can choose what speed to spin your wheel up to if you need to change how hard you shoot a ball, depending on how far you are from the goal, that sort of thing. And so this talk is meant to cover some of how some of the fundamentals of how you do that processing to figure out what the current state of the robot is. I will be largely focusing more on the things about just knowing the state of individual mechanisms on the robot in this particular talk, less so than the question of where is the robot on the field. That's something which I discovered last year is far more than a 1-hour talk. So decided this year, we haven't done this talk yet in a Spartan series, so we'll be doing that today. Now, there's many different ways that we can know where we are on where something is, whether that's the robot or not. One is modeling. You can just say, oh, we're applying some voltage or duty cycle to a motor for a certain amount of time. This is what should have happened. That only gets you so far, but it is an option. There's various types of encoders. These approximately tell you the current position of a mechanism or a rotational mechanism. Potentiometers, which typically give you a more absolute position of some sort of rotating mechanism. Various types of other stuff. And just to emphasize what we're covering here, this can also include stuff like cameras. They detect things. They tell you what the state of the world is. This isn't used as much in FRC, but you can have things like various motion capture systems that are typically used to give you a sort of ground truth for what a system does. The idea being that if you put little markers or radio tags or something on a robot and then have cameras set up all around a field, you can very accurately determine where everything on the field is. There have been some things like in that upper right where tags have been put on robots for collecting data about where they are in a match. That's not been used in sort of as a real-time feedback mechanism. It's been more used for experimentation and then some sporting desk analysis, I guess, of what's going on. But it's something that could someday be used. Also rather relevant are IMUs, which can give you, inertial measurements. I'm actually going to jump back to encoders in particular, since they tend to be very relevant for how these things work. Can anyone here describe to me how an optical encoder works?
You have a disk with the various cuts in it and an LED. The LED shines through the disk. It's a photosensor. There's a squaring circuit, and you read the output, either PWM or POP or otherwise.
So, as you said, the way that optical encoder works, you have its disk. This image, for some reason, does not actually show up properly. But you have a disk with a bunch of slots in it. You shine a light through it, and as the disk spins, those go on and off, and you can count those, how far you've spun. This does not actually give you exactly how far that the mechanism has spun at any given time. This gives you how many transitions between disks and not, or open holes and not, you have seen. all these sensors are imperfect. Nothing gives you the true state of the world. An encoder can be subject to the fact that you can't tell where you are in between transitions in the lights. You can have electrical noise on just about any of these sensors that can introduce issues. I should go to here to discuss that. You can have situations where the thing that your encoder or whatever is attached to is not actually directly the thing you care about. You probably have it attached to some shaft which may be a gear ratio or two away from where the output mechanism is, and there may be backlash. It may be the case that when you move the output mechanism, it can move a bit before the encoder starts turning. You may have the wrong gear ratio in your code. You can have all sorts of issues along these lines. And what that means is that you cannot directly use the sensors that you are reading. You cannot say, oh, this encoder spits out a certain position. No, this doesn't show up. This encoder spits out a certain position, and we're just going to use that. Or, oh, the RoboRio says there's a certain velocity coming out of the encoder. Encoders don't measure velocity directly. They don't measure how fast something is spinning. They measure the number of cuts they counted. And so whenever if you're trying to control the velocity of something, you need to understand exactly what it is you are measuring and what it is you are going to end up controlling if you try to use a certain measurement directly or indirectly. Yeah, just to cover this, I'll cover in a moment. But there's a lot of different types of errors you can get. There's a lot of ways to categorize them. These are just some of the ones I wanted to mention here. As another example, this is a plot of some data that came out of our robot this year. This is just me picking a random log out of the robot. These are the same mechanism. They aren't on top of each other because of various reasons. The line on the top is a potentiometer. The line on the bottom is a quadrature encoder. And it's not perfect. You can see there's little blips in the potentiometer. I don't actually know what that little blip right there is exactly, but it can be due to electrical noise. It's also the case that there's a bit more noise if you squint at this. The potentiometer is generally subject to greater imprecision than the quadrature encoder. So if we try to use this directly, this would be sort of close. But then what happens if we get here and we see a blip? What happens to we don't want the mechanism to suddenly jump. So your choices of sensors matter, is all that's saying. There's really something weird about my color saturation. This line is what happens if you take the speed number that comes directly out of the WPI line, or to be more precise, directly out of the RoboRio FPGA, I believe, the speed number for an encoder. Does this look like what the mechanism is likely to be really doing on a robot? Yeah, it really shouldn't be. And now, who knows? Maybe it really is, but it's not. I promise you, it's not. There's a few different reasons this can happen. One of the reasons is that, like what I was mentioning, an encoder cannot directly measure the actual position it is at. It is measuring the number of counts it got. And so if you are at 2 points, if you sample the encoder at 2 points in time, and then the way that you would typically get this sort of direct number is you take the difference in those two samples, you divide by the time at which the difference in time at which the samples are taken, and you put that up here, you'll end up where maybe on one sample you get a higher than expected velocity because you just managed to tick over a pulse. And on the next sample, you get a lower than expected number because you were about to tick over a pulse but hadn't yet. And so you can get these jagged lines. And if you try to then control the velocity of a mechanism based on that, you'll be outputting really jagged outputs. And that, while some simplified models of the world might say, oh yeah, that's fine, it'll just average out in the outputs, in practice, that's not what you want. In practice, if you send those sort of squiggly outputs out, then your robot will not be happy. Your mechanisms will jerk around. It'll not be very precise control. It'll not be great. And this is just in this case, our estimate of where the mechanism was, I believe this is actually a drivetrain encoder, our estimate of what the velocity of the mechanism was this orange line, which does not exactly match the it smooths out the noise. It gives you an idea of how much gets introduced from the encoders. I think there's some spots where, like here, where our estimate is actually well below the speed of the encoder, where that could be the wheel slipping, and so maybe our estimate is accounting for the wheel slipping, which is yet another category of error you have to deal with. So it's more than just smoothing out the jitter. So how can we do this? There's a variety of options. You can ignore it. This is a reasonable option in some situations. You may not care that much about precision, but you still maybe want to have a sensor doing something. That's probably not the answer you're looking for if you're watching or listening to this talk, but it's sometimes valid. You may be able to buy better sensors in some cases. You can't magic information out of thin air. You need a sensor. You need something to give you information about what's going on in the world. Like, the reason that this is a problem is not because the sensor is itself giving bad data. It's that using the sensor in a naive way doesn't give you the data that you care about. But you can buy better sensors. That is sometimes helpful. You can build better mechanisms. Like if you have a whole bunch of backlash in your mechanism and your encoder is, if you have something like a really wavy mechanism and what you care about is where the end point of the mechanism is, and your encoder is back here, then you're going to have trouble controlling the end point of the mechanism because you don't actually know where it is. So if you can build a stiffer mechanism, then your encoder or whatever sensor you're using will give you a better idea of what is happening. Or you can do things in a completely different direction, make it so you don't need to care where you are. You can build mechanisms that are mechanically self-centering, where when you go to, say, pick up a game piece off the ground, you don't need to worry about setting your intake to the right height because maybe when the intake drops down, it just rests on some hard stop so that it's at the right height. But then that's harder to adjust if you want to change the height later. If you have electrical issues, you can improve your wiring sometimes. That's not typically teams' issues if they're trying to make their mechanisms more precise, but it can be relevant. You can also solve it in software. The warning being that, as I was saying earlier, you need the data. If you don't have useful data, you can't magically make your estimates perfect. However, you can make the raw data that you're getting more useful. You can basically say, oh, I don't care about the really high frequency aspects of this data that cause it to jump up and down, so I can do filtering to get rid of that. And that implicitly means you're sort of losing information in one area, but it's probably information you don't care about. What you can do beyond just the sensors themselves is use prior knowledge about your mechanism to guide how you use the sensor data. You can use the fact that you know what motors you're using, what outputs you're sending to the motors, what the mass of the mechanism is, what the gear ratios are, all that stuff to improve what your estimate of the state of the system is. And just the final note on that, any choices you make with regards to filtering, you're implicitly making choices about and assumptions about how the system works. Like if you choose to not do anything and just use this estimate for your speed, you're implicitly assuming certain things about how the world works. Even if you say, oh yeah, I'm just doing the lazy thing, you're still making choices. So when you go to choose how to process your data and how to make use of it, you need to ask yourself questions about what you care about, because otherwise you will just go in and potentially do the wrong thing. How soon we need to estimate can actually mean two things. That can mean, well, that actually has to do with this bullet as well. What I was referring to here is when the robot is running, how quickly do you need to make use of the information you're getting? Like, do you need to immediately be able to take the information and use it to update the outputs you're sending to the motor to control the mechanism? Or is it something slower? Do you have a auto sorter where, like in 2022, you had different color balls because each alliance had their own color of balls, and so you might want to detect if the ball it just intook was red or blue and reject it if it was the wrong color. In that case, you have a bit of time. You can get a sensor reading, say from a camera or from a direct color sensor or the such, and take a large fraction of a second to determine if it's red or blue. That's very different from running a catapult directly off of a motor where a few milliseconds may be a relevant time scale for choosing what outputs to send to the motor. There's what do you care about for accuracy? A nice example of this is when you're in a game where you have to aim things, you generally care more about the angle at which you're aiming rather than exactly how far away you are from the target. That's not always true. That's a common situation. Where must it run? This can be useful for determining how complex of code you can write. Like if you have to make something run on the Rio, you typically have less processing power than if you're allowed to run it on an off-board processor. When does robot have to be done? You can't spend your entire season developing one random sensor filtering algorithm. Well, unless you have enough people that one person can spend their whole season doing that. So you need to eventually have things working. And then there's a question of sort of reliability of, okay, if we're building this fancy estimator, how wrong is it allowed to be? If we get a horribly wrong estimate back from it, what happens? Like if you're trying to control an elevator at a really high rate and you suddenly get a really wrong estimate of where it is and you slam the elevator straight into a hard stop and break the robot, that's very bad. If you're in the case of the 2022 game and you, to my earlier example of red versus blue bulls, if you misdetect whether you have a red or blue bull, that can be bad because you miss scoring a few points in the match, but you probably don't permanently break your robot. So understand what your requirements are. I'm sure you can come up with plenty of other potential requirements. So I'm going to start jumping into some of the particulars of how we approach things. This I'm largely, as I said earlier, approaching from the perspective of controlling mechanisms. A lot of this stuff corresponds to the base of what we use for instance, our robot localization, but that has a lot of extra complexities. So, as some terminology, X will refer to the state of our system. So whether that is an elevator or an arm or a intake wrist or something like that. We'll use Z to refer to a measurement or sensor reading, the value you get out of encoder, the thing you get back from a camera, whatever. We'll distinguish between, because it's common to do so, between the estimate of the system and the true state of the system. You will only ever know your estimate of the system. You never know the true state of the system, but it's useful to talk about how these two diverge. And then lastly, we'll have something that we refer to a bit, mostly when we're talking about Kalman filters, of the covariance of, the covariance of a variable. So if you are not familiar, actually, who here knows what a standard deviation is? Okay. When you have some variable, particularly course that is randomly distributed, which generally applies in this case, where we don't know exactly how accurate we are. We have noise in both the physics of the system, it may do unpredictable things, and we have noise in the measurements we get back. That means that, for instance, let's take a simpler example, Z, the measurement we're getting. There may be just noise in the raw measurement. Let's say it's electrical noise on potentiometer that's causing the analog value that we read to vary. That noise will have some standard deviation that describes the magnitude of the noise. There are also generally going to be other properties that make this the standard assumptions one makes in some of these filtering discussions not correct, but the typical assumption we make is that the noise is Gaussian, which means that it fits a normal distribution, which, if you do not know, is one that broadly speaking looks like that, where that may not mean anything on its own, but if you have like zero error, that's the most likely case, and then the odds of having large error drops off as you get farther away, and one standard deviation corresponds to generally about here-ish, where 2/3 of the most likely 2/3 of error will fall within one standard deviation of your actual value. When you have multiple variables, and variance is the square of the standard deviation, and that is useful because of how some of the math works. when you have multiple variables, so if you have a state of your system that is, say, the position of something and the speed of it, which is typically what we end up having, we typically care about, say, the position of an arm and how fast it's moving, then the errors in those two states may be related. So for instance, if you are estimating that the system is moving at 1 meter per second, and it is actually moving at 1.5 meters per second, then in all likelihood, your estimate of the actual position of the mechanism is probably also wrong. It is probably also too low, because if you're wrong in one respect, you're probably wrong in both. Because if you've been assuming that it's moving slower than it really is, and it will also have moved farther than you think it has. And so what a covariance matrix describes is the expected errors, both of each individual variable, as well as how they relate to one another. The idea is, so if you have a very high covariance between two variables, that means that they themselves are very closely related. And you could, in fact, have a situation where you have something like, let's take our example. If you had, well, that's actually not a great example. It's a really boring example is if you have two random variables, x and y, and you say that y equals x, they are very well correlated. Now, each individually, it may be the case that x is a normal distribution with a mean of 0 and a standard deviation of some sigma, which is fine. Y will also be like that, and then the variance of each variable individually will be sigma squared. Sure. But if you were to write out the covariance matrix, the diagonal conceptually, if the actual variable you care about is x, y, then the covariance matrix will have the variances individually, and then the off-diagonal terms, rather than being 0, which is what you would have if they were entirely separate variables, they will be infinity? I don't know. I can't remember what they would actually be, if it's infinity or if they would end up being sigma squared. I'm sure someone can correct me, but you very rarely need to care about the exact values, but it's good to be aware of. So let's jump back from talking about variances and talk about what you would probably arrive at if you were just trying to get rid of this up and down. What would you, the first thing that I think most people would jump to would be something like this. This is sort of a long-winded way, well, slightly long-winded, of saying the estimate we're going to have right now, well, is going to be a combination of our previous estimate at the previous time step, plus our measurement, and basically a weighted average of those two for some number alpha, which will describe how the average is weighted. So if your previous estimate of the system is that it was at a position of 1 meter, and then you get an encoder reading saying that it's at 2 meters, and then you would take a weighted average. If you had an alpha of 0.5, that would mean you'd weight the two equally, and so you then assume the system's at 1.5 meters. You could adjust that so that you trust, by adjusting that alpha term, you can make it so that you really trust the existing estimate more than future estimates, or vice versa. This smooths out the ups and downs here, but it has other suboptimal properties. For instance, let's say you have a mechanism that's following this is part of a sine wave. And let's say that yellow is the actual position, and the green is you applying this filter for, I don't know what alpha I chose to generate this chart. It's not really important. What will happen is that your estimate will always be a bit delayed, because you're combining past information with current information in order to find out where you are. And so if your mechanism is sitting still, that's totally fine, because then you'll just, if it's sitting still and you have no way of knowing that it'll ever do anything but sitting still, then great, use this estimate. But if you know it's going to be moving, then you'll always end up being behind because you'll always be combining some amount of past information with some amount of current information. There's other properties associated with this particular type of filter, well, actually, all filters, that I will not go too far into because that can be the subject of entire signals courses in college. But suffice to say that this ends up being imperfect, but gets you somewhere. It may be adequate for your use case. You can come up with other things along this line that are also helpful. You can make this much more complicated, but still be in the same vein. And get closer to what you want, but that's a lot of work. Let's see, what did I miss saying? Yeah, it takes a lot of time to get them to work well, because how do you choose this alpha? You need to go mess with your sensor. If you don't have a model of how the sensor works and a model of the system, it's hard to choose the alpha. If you do have a model and you can use it, then you're doing a lot of work, which may be fine, but then you may as well do something more complicated to begin with. So they can be hard to get to work well and are not always actually what you want. Also, like as I said, you aren't using the fact that you may know how the system works. Maybe you don't know how your system works and you have no better option, but you probably do. You probably at least know that when you apply a voltage, your mechanism moves in one direction or the other. So let's talk about Kalman filters. This is a bit of a jump, but it is what we now use for most of our mechanisms. It is the underpinning of, I think, what most people are using for localization who do it in FRC. I believe there are classes available for using the WPI and the such that allow you to use Kalman filters for estimating positions of things, although personally I haven't used them. The goal of the Kalman filter is to provide the best or most optimal estimate of a linear system that has Gaussian noise in both the system and the measurements. I'll try to define some of those terms in a moment. But the basic idea is that you use the fact that you can model the system, that you know what it should be doing, combined with the fact that you have sensors and you know how those relate to the system and you know what characteristics those have, to estimate what is going on and to avoid things like this where you have delays in your estimates. They are easier than I think some people assume to implement, because it turns out that the proving that they are the correct thing to do, if your system is actually truly linear, which virtually nothing really is, proving that can be difficult, but the actual equations are a few matrix multiplies, which choosing what the values of those matrices are supposed to be can be a bit of extra effort, but so is choosing what this alpha should be or the such. So let's talk about what I meant by a linear system with Gaussian noise. If our actual system of the robot is something like this, and I'll have an example in a moment, where the state of the thing, that's position, velocity, both, God knows what, is a purely linear function of the prior state, whatever the input to the system is, which in the case of FRC is typically a motor voltage or motor current, plus some random variable that is normally distributed, as I was showing before with the hump. And if your measurement is also a linear function of the state, so for instance, a very boring linear function, and I can just show this from here, is, well, that's boring. That's actually hard to see. Is if your state is your position, and so is your measurement, then z will just equal x. And that's a linear function. Oh, sorry, plus your random noise. But it's linear. Typically, things are really that simple for things like FRC, where you are pretty directly measuring one of the states of the system. They can be more complicated. So we've typically used that as a voltage. With brushless motors becoming more common, that can also be, say, a motor current if you're using the current control mode. If you had something that wasn't just a mechanism, it might be something completely different, but yeah. Yeah, and I'm saying input because that is the term that is used to describe this. It is an input to the physical system. It is not the input to your filter in the way you might colloquially say input would be the sensor readings, which are the output from the physical system. So pardon if the terms that everyone seems to have decided to use may or may not be intuitive. All right. To describe what some of these are, F and B are basically come from the physical model of the system. They are describing what will happen if you apply a certain voltage or don't and let the mechanism move. H in this case is how the sensors relate to the current state of the system. And then I didn't write them here, but you will have parameters Q and R to describe what the distribution of these noises are. So for instance, if you are really unconfident in how your system will evolve, or if there's a lot of uncertainty because you are driving an intake that may have a really bad gearbox, I don't know, then you might have a really high process noise because it will do unpredictable things. If you have a sensor that has a lot of randomness in it, if you have a really low resolution camera and it gives you really flaky readings, I don't know, you might have a very high sensor reading noise. If you have something that's much more precise, if you have a really high quality gyro and you're estimating the yaw of the robot, then the noise on your sensor reading might be quite low. I will note that F and H, you see in our code base and in a lot of places, these will be A and C respectively. I'm using F and H because that's what appears on the Wikipedia page. And I didn't feel like rewriting all these equations in Google Slides. To take an example of this, let's say you had a flywheel. Your state might be a position and velocity. Now, you might not, if you have a flywheel, you probably don't care about the position of it. The reason we care about position, though, is because you probably don't have a sensor that directly measures velocity. It is possible to have sensors that directly measure velocity. For instance, if you have a radar, it can measure the Doppler effect of the radio waves bouncing off of things, and that gives you velocity reasonably directly. That's not the case for an encoder. As we were talking about before, an encoder is measuring ticks, so it's not even truly measuring position, but it's close enough for this. We'll say for simplicity's sake that your U is a torque that directly corresponds to current with DC motors. Yeah, and your measurement will be an encoder reading. And let's just step through these matrices. This is both, I'm not going to go too much into detail about how to derive these because some prior Spartan series talks do go into how to derive these. I could talk a bit more about these depending on where we end up on time. But basically, if you look at your F or A matrix, we're saying that, I don't know if everyone knows how matrix multiplication works, but in lieu of describing that, the one is just saying that if nothing else happens, the position will stay the same from one point in time to the next. It doesn't randomly jump. We have a DT term here. This indicates that the position will change. You'll have some time step out. You can't run this infinitely fast. You can't run your filter at every picosecond or whatever. You'll run it at, I don't know, 100 hertz or something. And so what this says is that if you're at 100 hertz, in that 10 milliseconds, the position will be incremented by 10 milliseconds times the speed at which the mechanism is moving. You then have this term that says the position should not impact the velocity, which is generally true. This may not be true if you have a literal spring on something, which isn't totally uncommon. And then some number that depends on the physics of the system. And that's what you would have to go to the other talks to see how to derive. And I just put in 0.99 here because it's plausible. That describes how the velocity will decay over time. So basically, if you're applying no voltage to a motor, what will happen is that over time, it'll gradually slow down, and that's what that is describing. This term on the U is saying that if you have a non-zero voltage or current or something, the position will not be affected at that higher rate by it. It'll technically be affected because it should move a bit farther forwards because of it, but the more direct impact will be on velocity. If you have some, again, this is a number that will depend on the attributes of the system, and then plus your random noise, and then this is just saying only pull out the position from the current state to get your measurement. Q, U, hand wave to pick. There are principled answers here. You can sometimes get a reasonable answer for what R should be. Like you might be able to just look at one of your sensors and see how noisy it looks. Honestly, where we generally start is just we write out a diagonal matrix. We assume that our noises are uncorrelated between different states because the first approximation, most of them are. And come up with numbers that seem fair. And then we'll adjust them once we see what it looks like in the real system. This is, as I said, not the most principled, but unless we're going to perfectly characterize how good our model is from the start, we can only get so far. Yeah. I was going to go through describing an alternative, or constructing a second example, but I'm going to skip that and describe how the rest of the Kalman filter works, and then we can go back in and talk about more examples. And we'll just leave that bit of red there. These are all the equations you need if you actually want to write the code. It's less than it looks like. You actually can ignore like the last one. This is just from the Wikipedia page because they had the equations formatted correctly and it was convenient. And these in the right here are all equal signs. I realize it's a bit washed out in this projector. I do not know why. All this is saying is that if you say it is most convenient if you have all your sensor readings coming in at the same time that you care about generating an estimate. And if you have that, then you can just run through this list essentially. And that's common for our use case at least, where you have a elevator or a flywheel or whatever, where you get a reading and then you immediately want to know where you are so you can choose what to command the motor to do. The first thing you'll do is you'll just update your estimate of the state based on what your prior estimate was from using your model of the system. You'll literally just say, here's what I think happened in the last 5-10 milliseconds. You then have to update your estimate of what the current covariance of your estimate is. What this is trying to accomplish is saying, okay, we are dead reckoning based on the model for the past few milliseconds. This means we're more uncertain about what the current state of the system is, and we have to capture that the rest of the filter needs that to be able to determine how to use the measurement to influence things. Like if you have a very high uncertainty in where you currently are, you're going to want to trust new incoming measurements a lot. If you're very certain about where you are at a given point in time, you can choose not to trust incoming measurements as much and use that appropriately. This stuff just what this means ends up just coming out of the derivation of how a Kalman filter works. The important thing to understand with this is that when you're doing the update just based on the model, it always ends up increasing. Well, sorry. It typically ends up increasing. It does not necessarily always end up increasing. There are subtle cases, actually not always so that's that subtle. If you know that your flywheel will always spin down to 0 if you don't apply any input, then you can be reasonably confident that if you say start by not having any clue how fast the flywheel is spinning, you can be pretty confident that over time it will not be spinning as fast. And so in certain cases, it is actually possible for the covariance to go down, but it won't go down to 0 unless you have a perfect model. And if you have a perfect model, then you shouldn't be using filtering. You should be making lots of money somewhere. Then you use the sensor readings. So the first thing you'll do is you'll calculate how far off of your expected readings they are. So what this is saying is you got the actual readings from your encoder. You know what you expected to see. What's the difference between them? You calculate that difference and you use it a few steps later. You then do some magic nonsense that gets you what gain you're going to use. What this is basically saying is given the sensor noise, or what you believe the sensor noise to be, and given your current estimate of the covariance of the system, how much should we update things by? And if you write this out more completely, what you'll realize, there's an inverse hidden down here. I'm just going to grossly abuse some matrix notation here, but you'll have H, P, H, T. Oh, sorry, that's not the direction I intended to do that. On the bottom, you'll have H, P, H, T plus R. And in the top, you'll have your P, H, T. This is, as I said, grossly abusive of matrix notation. But the important thing is you're ending up taking the inverse of R. What this is basically saying is that if you have a sensor that can get perfect readings, your R ends up being 0, then you can perfectly trust it, and this number will be very high. And what that K is then used for is, in another moment, you update your state of the system based on K times that Y that is the error in the expected value. And so if this number is if this K is much larger, for some definition of larger, then you will trust your sensors more. If you really don't trust your sensors and your R is very big, then this K will go down to close to 0. The same thing will happen if your P is already very small relative to R. It'll be very near 0, and so you will just not really use your sensor reading all that aggressively. Yeah. And then the Wikipedia page throws in an extra step where you calculate what the difference between the measurement and the expected measurement is after having done all these updates, but you don't really need to do that unless you just want to see how big the update was, which is sometimes nice. Yeah, this is just more white space that I was going to use for talking about stuff. Yeah, that's the material I had already. I was going to see what questions people had and where people took things from here. I talked at you a lot.
Can you give an example of where you use this in the code?
I could give you a sample of where you use this in code. I could also give you, well, I'll give you two things. I'll show where we use some of this in our code, but that's a bit hard to follow. I could also basically write out what this would look like in code. How do I get over here? Oops. So, yeah, it's fine. I'm going to open a Python file just for sake of convenience. If you had something like, if you have NumPy available, in C++ or Java, you can find matrix libraries. And then you can have something like, let's go up a few slides. I wonder if that's, I think I know what the issue might be with the color saturation, but I'll worry about that later. Let's take this example. You can literally define some sort of Kalman filter class. And let's say dt equals 0.1. And I just picked 0.99 arbitrarily. You would do, actually it's the same math that's back on that whiteboard back there. But anyways, to figure out what the model is. And your B would be something like, number that's near 0, and I just picked 0.1 out of purely arbitrarily. Actually, I'm curious now. Huh, okay. And then your, what do we call it? H is, and we were going to choose arbitrary values for our Q and R. So what do we go with the identity matrix for both until we can think of anything better? And R is a 1 by 1 because we only have one reading. That gives us our constants, and then you could have something like, on each update, we have motor readings, so some motor torque, and we have a encoder reading. And when that happens, you want to go through all those equations before. So you'll maintain some estimate, x hat, and let's say you start by assuming it's 0. You might have some other thing you assume that it starts at, but let's say 0. Then you can first update your estimate. So you do that f times the prior value plus b times your torque. And that's the first step. That is, that's this line here. Then we also need our current estimate of the covariance of x. And we'll just start with something. It is common to lazily assume that it starts at q, at least in our code base. What will end up happening over time is that if you look at these equations, p never depends on the current value of x or the current measurement. Like in this first estimate, it only depends on itself, f and q, which are constants. And then in the update that happens down here later, it only depends on k, h, and p. P is itself, h is a constant. K, again, only depends on p and other constants. So what you can actually do, what actually will end up happening is that when you go through those equations enough, it'll end up converging on something. And you could pre-calculate that if you want, but either way, the starting value doesn't end up being critical in this sort of case. Sometimes it matters. Anyways, we then do that update of, what was f times p transpose. I don't remember how NumPy does transposes, but I'll assume it's basically that. And then, so that's the model update step. Then we need to do the measurement update step. So first off, we calculate the residual. Encoder reading minus h times x. And then we do the remaining equations. And let's remove that. And k equals p times 7. Oh, and the question, since I realized it wasn't caught, was, could you show an example of what this looks like in code? And let's see, h transpose s inverse. I actually think in NumPy that's and then it's just a matter of updating your x hat again, which is an identity matrix. I have no clue how you generate an identity matrix in NumPy. Sorry, that's the p update, my bad. The x hat update is and that's Kalman filter. There's the picking these numbers is not trivial necessarily. Then you need to actually fit this in with your robot, you need to have, you need to call the code somewhere. Like this Python code probably wouldn't fit into your robot directly. But when it comes down to it, it's just you write some lines, you define some constants, and as long as you define the right constants, you're good.
How do you do that, defining the right constants?
That's where the prior Spartan series talk comes in. So some of these are just, you have to go through and, well, figuring out what states to even use in the first place, like knowing you want to use position and velocity is not actually always trivial. Sometimes that is very complicated. For most simple mechanisms in FRC, position and velocity end up being what you care about. The rest of these come from the model of the motors. So I would, and of the parameters of your mechanism. The resources I would advise looking at for that are for some of the, as I said, there's a prior Spartan series talk that, I can't remember the name of it, that would have covered this. There is information, I believe, if you search FRC controls textbook, there is a very long document by Tyler Van Ness, who went through and wrote down how a bunch of this stuff works and how some of this modeling works. That is an excellent resource if you want to read this. There's a lot there, so you can spend a lot of time reading it, but it will provide you with information you need to know how to get those numbers. And some of it is sort of, you do end up needing to manually adjust the numbers sometimes, like it's, oh, the mechanism ended up being heavier than we thought it was. Some of these numbers have to do with like the moment of inertia of a mechanism or a moment of inertia of all the gears combined in a gearbox, which can be hard to estimate directly. So it's just like, oh, you do things like say, okay, we disable all the measurement updates. Like if you take this code and you just comment out all the stuff that uses the sensor readings, you can just get an estimate of where the mechanism is based on your model alone. And so you can do something where you run your actual robot, you apply 1 volt or 5 amps or whatever to the motor, you look at what it did, you presumably need to have an encoder or something attached to it most motors these days have encoders built in, so they'll tell you how it moved, and you can compare that directly to what running this would have given you, running just the model would have given you, and see where they diverge. If it's like, oh, we apply 5 amps and it consistently moves slower and less far than we thought it did, you might have a mass number wrong. If it's something else, maybe it's you just have a gear ratio wrong. I don't know. And that figuring that out is system identification, and there are some tools some open source tools for FRC that attempt to do that more automatically, where they will literally apply a voltage, look at sensor readings, and attempt to estimate what the mass of the system is, actually it's mostly just what the mass of the system is, and a few other attributes to figure out what those numbers would end up being. Using those correctly can sometimes be a bit of a pain, but they do exist. Further questions?
I imagine you do similar things like just measuring noise on a sensor.
Yeah.
That's one of, like you said earlier, that's kind of a hard one to get.
Yeah, and the problem is if you just look at a sensor and just measure noise on that alone, that may not actually be what you care about. Like you may get issues with the backlash on the mechanism means that you fundamentally can't trust it as much as just if you take all the numbers. If you take the sensor and you just take the standard deviation of a bunch of numbers, that may not be what you actually care about for the noise.
You kind of highlighted this earlier, but each of our actuators has basically this wrapped around it for controls, right?
Yes. And the question was, or comment was, each of 971's actuators basically are using something like this for the controls. We previously used a different estimator, which did use the model of the system, but did not actually directly input these noise numbers. we moved to this because like once you write the code, it's easy to reuse it in a bunch of spots. But basically, it's, yeah, we already want to estimate all these numbers so that we can choose the control loop gains. Like you want to know the model of the system so that you can choose the control loop or design the control loop for how you drive the thing to the right spot. And that's why the prior Spartan series talks include discussion of that, because those are about the control loops themselves, less so the estimation. And so once you have those numbers, then you just feed them in and you get a pretty good estimate to begin with. Like we don't end up having to spend a lot of time tuning this for most mechanisms. We spend a lot more time on like the localization and stuff, but for most of the mechanisms, it's like get the numbers about right and it's pretty good. That's in part because encoders are very good to begin with. Yes, they have some of that noise when you're estimating velocity, but beyond that, if you have a decent encoder and your mechanism is stiff and has low backlash and everything, then you're in a pretty good state to begin with.
How does machine learning help with improving the coefficient?
The question was, how does machine learning help with generating better numbers and better estimates? We haven't used that any machine learning very directly in this. You could, in theory, for simple mechanisms, the way they work is pretty well known, so you don't need, well, your machine learning might be a pretty simple thing that just fits a single number. That's what some of the system identification tools that some people have built for FRC do. There are some interesting possibilities for more complicated mechanisms where it may be harder to characterize the model. Like if you have something where there's some weird game piece interaction or the such where it's just, it's hard to describe exactly what's happening. Like these models are great if you just have like a flywheel that's spinning and has no special friction. But if you have a flywheel and you, for some reason, need to model what happens like as the ball goes through the flywheel, then it's much harder. Now, typically you don't, because the ball goes through the flywheel much faster than you can do anything about it. But you could have something where it would be interesting to try to say learn some model for what happens when that goes on. We haven't had any situation where that's been necessary, but yeah. Yes, Max?
So I know for ARM, we did something called an extended Kalman filter. So what is that?
Yes. So this gets into sort of what we use for localization and such. I asserted previously that a Kalman filter is appropriate, or it provides the best estimate for a linear system. If you do not have a linear system, which in many cases you do not, you can still sort of use a Kalman filter and it'll be pretty good. What ends up happening is that rather than necessarily defining like these constants directly, you take a more complicated nonlinear model of the system and you linearize it at each given point in time. And so you choose, effectively you're calculating the f and h and all that gives you the closest possible linear model of the system at that point in time. You then run all your calculations, and then at the next point in time, you update all the constants again. And it ends up being pretty good, even though there's not much theoretical justification for that being the best option. It turns out that it's still pretty robust to most cases. Thank you.